Welcome everyone. So today we are going to discuss about this technology mapping for FPGA. Specifically, we are going to talk about the basic FPGA structure, what are the components of FPGAs, and then we will talk about the technology mapping for FPGA, specifically LUT mapping, DSP mapping, and RAM mapping. Okay. So if you look into the FPGA field programmable gate array, which is basically a prefabricated silicon, right? So it's already fabricated, but the advantage is that it's electrically programmed in the field, and it can almost implement any kind of digital circuit, right? So it's already have a fixed structure, component all are already fabricated in the board, and you can actually map any kind of logic circuit into that. The advantage of this FPGA is that it's very fast, right? The time whenever you have a RTL, you can easily just map into this FPGA using some synthesis tool provided by the industry like Xilinx, Altera or Synopsys Cadence, and you just use it, right? So you don't have to, on the other hand, in the ASIC flow, you have the whole process is very time consuming, and it does not make sense to have a when you have the number of chip you record is very less, right? If you just need one or two kind of thing, kind of chip or design, you don't need to go for ASIC because it's a time consuming process, and it's a costly also, right? So that's why FPGA is very popular because low time to get it done, and it's very popular in prototyping also. Before making the actual ASIC design or actual chip, we just map it to FPGA and see whether the simulation is giving correctly or not, whether your design is working correctly or not, right? So FPGA is very popular. The disadvantage of FPGA is that it's little bit slow because it's a programmable interconnection, so it has all the possibilities inbuilt, so it is slow, also power consuming, and also larger compared to the ASIC design. So for a given design, ASIC design will be much more smaller than a FPGA design. But because of the other advantages, FPGA is widely used in EDA industries. Okay. So if you just look into the FPGA in detail, so it consists of so this is the kind of overall structure of a FPGA. It consists of sets of logic block, configurable logic blocks. They are just run in arrays, and they are interconnected through these interconnection units, right? So these are the interconnection units, and the IOs are placed usually in the outer interface, right? And this configurable logic block is basically is configurable, so where you can actually map your design. So it consists of both storage as well as the logic units. So your design has to be mapped here, and the interconnection has to be done through this interconnection unit, and all this logic block is programmable as well as this interconnection is also programmable. So you can make connection from anywhere to anywhere, right? So anywhere the connection can be made through these interconnections. Okay, and primarily this programmable component are mapped through SRAM based programming technology. Also in some scenarios this can be flash based programming technology or anti-fuse programming technology. Okay. So if you look into the CLBs, configurable logic blocks, so it consists of, this is the primary component where your design has to be mapped, right? So it consists of primarily a cluster of basic logic units, which is nothing but lookup table. Okay. So and also it consists of some memory also, just to store for storage like flip flop and all, RAM and all other components, right? So essentially this LUT lookup table is the building block of an FPGA, because this CLB consists of several 4 to 8 LUTs or maybe more in modern FPGAs. Okay. So if you just look into this LUTs, is basically lookup table, right? So it consists of a memory which is SRAM based 1-bit memory, right? And it has some inputs, and it decides which memory bits should go at the output, right? And it also have a register at the output. So based on the number of such input select line, we say it's a 4 input lookup table, right? So 4 LUT. So basically K LUT depends on the number of inputs, right? So what does it mean? So a LUT, if it has a K input, if K input LUT can implement any Boolean function of 2 to the power K, right? So possibilities of bits are there. So any Boolean functions of K input can be implemented here, right? So if you just think about a Boolean circuit, it consists of maybe 100 200 gates. It has K inputs 1 to K, and one output. So that Boolean circuit, it consists 1000 gates. It doesn't matter how many gates are there. So it's you have to just capture the input output correlation, right? So if the input is 0 0 0, then what is the output, 0 0 1, what is the output, and so on. So basically you need that table for where all possible input possibilities are there and corresponding that output, right? So that is the output bit, and this output will be stored in this SRAM, right? And when your input is say 0 0 0 all zeros, then the output is 0. So this bit will be coming at the output, right? So this is how that your Boolean circuit will be implemented. So it's not that all gate will be mapped here. We capture the functionality of any Boolean circuit where we have k inputs, one output. That particular possible all possibilities of output will capture and will store that data stored in that SRAM, the memory bits, and this select line, the inputs will actually select which bit has to be the output, which output should come at the output, right? So that is something is lookup table. And so primary component of this CLB is a lookup table, and also if you just look into the interconnections, I also said ki these interconnections are also programmable. If you look closely on that interconnection, so these are the CLBs, right, and the interconnections we have switch box as well as circuit box, right. So the switch box, if you look into this, there are interconnections either bidirectional or normal, all possible directions. So you can understand here. So whenever some data come, it can go this way, that way, and all the possible ways, right. So these are the controllable. So if you just set this bit is 1, then this data will go this way. If you set this bit is 1, then this data will go this way, and so on. So if you just set this one 1 and this 2 0, then this input will come and go through this way, right. So this is so this is how the whole circuit is implemented, like this, bidirectional and unidirectional. So so these interconnections are has to be programmed also, right. Based on the actual interconnection, we are going to set these bits 1 or 0 to make the actual interconnections, right. So this is how the overall structure of this FPGA. Okay. So this if you look into an FPGA, it does not only consist of LUTs. So this CLBs consist of several LUTs, and also some of the CLBs are DSP unit, right. So if you just look into this one specific structure here, you can see that a column specifically used for dual port RAM. There is another column which is specifically used for DSP, right, DSP48. So that means in this overall structure, as I said, these are all CLBs. Some of them will be used specifically for DSP, some of them is for RAM, and some of the other is for logic units, where is basically we have this logic this lookup table based structure are stored. And in a CLB, we do not have only one, we may have say 10, 12, 14 number of logic units are stored together and they are interconnected, right. And also one register is there, just to we can use that register also to store some data also, right. So this is the overall structure of a DSP. If you just look into the connection of FPGA, if you go into the DSP structure, so DSP is basically is a very fast implementation of a multiplier. So if you just look closely in the DSP structure, if you can see here in the DSP block there is a multiplier, right. So the primary purpose of this DSP unit is to perform the multiplication in very fast way, right. If you just map a multiplier into this lookup table based design, it will be very big and it will be slow. On the other hand, it is a fast implementation of a multiplier, and this is fabricated within the FPGA board itself. But in the DSP unit, it is not only a multiplier, it can have a pre-adder, it has also have set of latencies, right. So we have 3 set of latencies here, and this is MAC. There is a sum, right, S equal to S plus A, accumulator, right. So this is what is called accumulator. So you can multiply and accumulate, right. So multiply and accumulate MAC, right. So this is what is happening here. Also we have we can also do a post addition also, right. So this can also come here and you can do a post addition. So you can do specific type of operation, like you can do B into A, or you can do A plus D into B, or you can do A plus D plus minus, this is plus minus, and then you multiply this with B and then you add C, right. So all kind of possibilities are there. So all this kind of structure when you have in your design, those can be mapped to a DSP unit. And also you can pack some of the setup register also, 3 layer of registers are there. So, it has 3 latency, either you can bypass or you can use them. So, this is the abstract structure. In design you can actually bypass any set of registers also. So, this is what this DSPs, and also it has some memories RAM. So, where you can store the large arrays, large memories, large arrays, RAM and ROM. Also it has some shift registers. Okay. So, shift register in hardware, you know, there is a specific kind of register where you have the data in every cycle, you shift the data by 1 bit by left or right, left shift or right shift, right. So, in specifically in filter application, the shift register is widely used. So, some of the registers, I mean some of the memory is also shift register inside the DSPs, inside the FPGAs. So, so this is the overall configuration of a FPGA. And now, if you just look at specific case, an example Altera statics 2 board, you can see here this lab is nothing but the CLB. So, in Altera this lab is called as lab, sorry, CLBs are called as lab is logic array block. So, which is CLB. So, inside that, so you have series of labs, and these are the and some of them are actually smaller RAM, right. So, these are the smaller RAM, you can see this is M512 bits RAM. This is also RAM, sorry, this is DSPs, this is DSP block, these are again lab, and again there are smaller RAM M for 4K bits RAMs are there, and there is a bigger RAM also, right. You can see, and the IOs are here. So, these are also IOs. So, this is a specific structure for statics 2 block, and if you just see have some detailed data like, so this lab, which is basically CLB consists of 8 ALM, right, and each ALM consists of 2 LUTs. Okay. So, that means effectively in CLB we have 16 kind of LUTs. Okay. Also we have other input like the to dedicated full adder is also implemented there, a carry chain and a register chain, right. So, what is the importance of this carry chain? What is the utilization of this? Whenever you have a adder circuit, so it has a carry, right, and if the carry has to route through this circuit block to somewhere else, it will be slow, right. You want to execute the add in fastly, right. So, what it actually happen inside the lab, whatever the 16 LUTs are there, they are connected, right. So, their output are connected each other locally, not through the other circuit block. So, this is carry chain. So, whenever you implement a adder inside a CLB, that carry will not be routed through the switch box or circuit box, right. It will be internally connected, and it will be very fast connection path, so that actually you can do this additions fast, right. So, this is how this adder is also can be implemented in the LUT in faster manner. Okay. So, this is something the detail about the statics block. So, this is all I just talked about, just to give a brief idea what is FPGA and what are the different components are there inside the FPGA. Because when you are going to talk about the technology mapping, we need to know what are the components are there which can be used efficiently for your design purpose, right. Okay. Now, if we just look into our software flow, right. So, EDA software flow, we know this high level synthesis, then logic synthesis and physical synthesis, right. So, after logic synthesis, you know, in the physical synthesis we have this floor planning, placement, routing. So, in FPGA, whenever you have after the logic synthesis done, now you have to map your circuit into this LUTs in DSPs and this RAMs, right, because you do not have any gates in the FPGA board. So, whatever the circuit is there, how many gates are there, you have to find out. So, if you know your design has say k input LUT, right, so 4 input LUT. So, you have to figure out all possible such 4:1 kind of component or the pattern in your design, and that has to be mapped into that in a single LUTs, right. So, you cannot map all the gates individually one LUT, that will be more costly. So, we have to find a pattern and we have to map them into the LUTs. We have to find the multiplier, we have to map them into DSPs, we have to find the big arrays, we have to map them into RAMs. So, that is what is called technology mapping, and once this is done, then it will go through the normal procedure like placement, routing and all other stuff, because finally you have to map them into in the actual hardware, you have to place them into specific LUTs, because and then you have to also make the connections, which is routing. So, those are the normal steps as like ASICs. But in technology mapping, we have to do a specific structs which is specific to FPGA, and that is the discussion topic for today. So, we are going to discuss more on how to map a big circuit into FPGA, into LUTs, into DSPs, into RAM efficiently, right. So, that is what we are going to talk about today more. So, that is what is explained again here, that for ASIC the different is that we have a cell library, right. So, in a cell library typically we consider have a complete set of said like AND gate and NOT gate. So, through which you can implement any kind of gate XOR, XNOT, NAND, NOR, and any gate we can represent using NAND and NOT, right. So, and we have also set of registers like D flip flop. So, whenever you have a circuit where you might have XOR gate, you have some other gates, those has to be mapped through this set of gates. So, that you actually for ASIC you are effectively replacing all your gates using a standard library gate. So, that those can be those can be finally fabricated, because the library the fabrication will support only this kind of gates. So, that is for normal ASIC flow, but in FPGA as I mentioned we have LUT, DSP and this RAM and ROM. So, we have to that gate level design has to be mapped to LUTs, right. So, it is not 1:1 mapping that one gate will go to one LUT, then it is a huge design and that is wastage of your resources, right. Similarly, it is not that you have to identify the multiplier and that has to be mapped into DSPs. It is not only a multiplier as I mentioned, it can be MAC, right, some pre addition, post addition and different combination can be mapped into DSP. So, that has to be done. If you do not do it and if you map your multiplier to a logic gate or LUT, then it will be a your area will be exponential, and maybe if you have large number of multiplier you may not map your whole design into a FPGA. So, that has to be taken care. Similarly, this RAM mapping. So, the difference from this ASIC to FPGA in technology mapping is so in ASIC we have the cell library mapping from the normal gates to cell library gates mapping, and in FPGA during technology mapping we have LUT mapping, DSP mapping and RAM mapping. So, this is where it primarily differs, the ASIC flow versus FPGA flow. On the otherwise this placement, routing, all are kind of different, more or less similar algorithm has to follow. Okay. So, we are going to discuss more on these three today. Okay. So, let us start with the DSP. So, as I mentioned that the DSP unit is capable of doing many things, right. So, it has a pre-adder, we have a post-adder, we have this MAC summations and also we have 3 set of registers, right. So, the objective is to map maximum kind of substructure into this structure, right, because if you have also you just do a addition in this block, then also occupying the whole DSP. If you want to multiply only want to do a one multiplication here, then also you are actually occupying the whole DSP, because this DSP cannot be used for something else. Or if you just do the whole thing, right, if you just do B into some pre addition and then post addition and then you do the MAC summation, then also it is going to occupy the whole thing. And also if you just pack some register inside, then what will happen? The delay, because if you just have a path which consists of adder, multiplier followed by adder, it will be a big path, though it is very fast, but it is a big path. So, it is advisable that you pack at least some registers into this structure also. Now, the question is how we can do this efficiently, right. So, that is something is called DSP inference in the FPGA flow. So, you can understand once you have done the logic synthesis, in the after logic synthesis what will happen, everything represented by a gates. So, in that case it is very difficult to identify which is multiplier, which is adder and something like that, right. So, the problem is that we have to identify this multiply and equivalent structure before logic synthesis, which is called pre-map stage, right. So, before logic synthesis we have to identify this MAC structure efficiently, and then you have to preserve those structures, so that logic synthesis bypass those structures. So, they should not map those adder, multiplier, those structure into gates, gate level design, then we are not able to map those things into DSPs. So, the idea is here is that we identify those MAC structure before logic synthesis, preserve them. You inform logic synthesis that you should not do any kind of synthesis in this part of the design, and then during technology mapping you just map those circuit into DSPs, right. This is the overall flow. And again I just mentioned you try to find the as max structure possible, right. So, the way algorithm works is something like you identify all your multiplier in the RTL design, right. So, you identify all your multiplier in your design, right. So, then you can map that, but you try to expand that structure, right. So, then you try to find out some. So, you find initially you find only a MAC, only a multiply, then you try to find out whether there is any pre-adder or not. So, if you find a pre-adder, then your structure will be like this, right. and then you try to find out is there any post adder or not, right. So, this is also you try to find out, and then you try to find out whether is there any multiply and accumulate options are there, right. So, this is whether this is a multiply and accumulate options are there or not. So, if you basically just try to start from a multiplier and try to enhance the structure as much as possible. So, suppose you figure out this structure, right. So, you figure out this structure that I have this a pre adder as well as a post adder, then you can actually have this structure, right. So, this is the max structure we are going to preserve, and but there is no register here. Then the next objective will be you try to do some local retiming just to move some register nearby register. There may be some registers here, right, some register here, maybe there are some other logics here, but finally there is some register. You try to move these registers into this structure, you move these registers here, you move these registers here, right. So, register here, so that you can pack those registers as well as in the max structure. So, this is the overall idea, that we start from a multiplier, we try to expand that structure which is supported by a DSP, which is basically have a pre adder, post adder or a accumulate. Those structure, once you figure out the structure, you try to find out the nearby locations, what are the register available, can we move the register inside this structure. If you move this structure, then the whole structure will be faster execution in the DSP block, right. So, this is something the overall approach in DSP inference, and when you find the this big structure, you preserve it, you do the normal logic synthesis, and then you map this preserved structure into the DSP block during technology mapping stage. Okay. So, this is overall the DSP inference flow in any normal EDA synthesis, FPGA synthesis tool. Okay. Similarly, if you just go for memory inference, again it has to be done in the pre-map stage, because if you just map the whole array into this logic array, because logics in the registers, then it will be a problem. So, identify the big arrays, and then you preserve that, so that you can map them into RAM. Again, the problem here is something like the RAM has a fixed number of ports, maximum 2 ports, maybe one write port, one read port, or maybe 2 read port or 2 write port, right. So, this is the possibilities. So, based on the access pattern of that register, we have to decide whether this can be mapped to a register or in a RAM or not. If it has a lot of accesses in a same clock, maybe you have say 4 access to that particular array, then probably it cannot be directly mapped to a RAM. Maybe you have to do some kind of modification. Some synthesis tool does that. It try to break the whole array into 2 part, or you break column wise or row wise, so that that access can be differentiated, and we can create a block where we have maximum 2 access at a clock, and then we can map that whole thing into a RAM. So, those all the intricacies are there, I am not going to detail of that, but the bottom line here is something that you identify those structure, you make sure that your access is something which is supported by the RAM block in the FPGA, and then you try to preserve that and you map it into the RAM block during technology mapping. Also, there are other possibilities are also here, like if you have some asynchronous reset to that particular memory, right, then it cannot be mapped to the FPGA block, then probably you have to add some extra logic around the RAM, you map that particular big array into the RAM, and just to overcome that asynchronous reset, you add some extra circuit, right. So, this is your RAM mapped and some extra circuit that will talk about that asynchronous reset. So, those we will discuss in another separate section, but the overall idea is here, is not very obvious, just find and map it to RAM. There may be a lot of intricacies like asynchronous reset, how to handle that, you might have some extra logic has to be created just to handle that, or you have maybe have more accesses, then you have to probably split just to make sure that you have sufficient number of access which is supported by FPGA, and then you map it to the RAM, this RAM block of this FPGA. Okay. Similarly, that you have to find out the SIP register, identify the SIP register pattern in the RTL, you preserve it and you map it to SIP register. So, this is all is done. So, usually all these things are done before logic synthesis preserve, because after logic synthesis this structure may not be very obvious to identify. So, usually most synthesis tool does all these things before logic synthesis, but actual mapping happen after logic synthesis during mapping stage, but identification of those kind of structure is done before logic synthesis. Okay. So, now we are going to talk about this LUT mapping. So, LUT mapping is something lookup table, as I mentioned earlier, that this is it has 2 to the power k number of SRAM bits, and based on the input value we decide the output, which output should go at the output, right. So, this is how the lookup table looks like, right. So, if we just take a specific example, suppose I have this function. So, my output is like this, if a and b is 0 0, then output is 1, 0 1, then output is 0, and so on. So, I am going to store these outputs in this RAM, right, 1 0 0 1, and when my input, and this is the select line of this marks, when is 0 0, this bit will come at the output. The mark structure is something like that. When this is 1 0, this bit will come at the output, right. So, when the output is 1 1, then this bit will come at the output, right. This is how we are going to map. So, now if this is the primary part of the technology mapping, because you can understand in a big logic circuit where we have millions of gates, and our objective is to map all the gate into some LUT, right. So, this is the overall objective, and as I mentioned earlier also, when you just map one LUT into one gate into one LUT is not acceptable, because finally you are not going to implement any gate into this LUT. We are just implementing that input output relation, right. So, the idea is here is like you identify a big structure where it has k number of input and one output. So that you can map this k input into one output sub graph into one LUT. So, any size does not matter here. It may be a circuit where we have only k inputs and one output, and maybe consist of 1000 gates. It may be consist only 2 gates or maybe 4 gates, but the big structure, all the things can be mapped to a single LUT. And also there is important point here is that, so initially suppose there is a structure like this, right. So, this is a structure like this, okay. So, the delay of combinational delay was a delay of 1 2 3 4 5 6 gate delay, right. But if you map in this whole structure into 2k LUT, right, 2 LUT, that means 2 input LUT, then the delay of that particular thing will become delay of 1 LUT, because finally when you are actually executing this into FPGA, it is just 1 LUTs. So, it is very important to identify the maximum structure which can be mapped to a single LUTs, right. So, this is something we have to do. So, if you just think about how the whole mapping idea works, suppose you have a circuit like this, you try to find out this kind of a substructure, right. So, you try to find out a substructure, and here input is 1 2 3 4 5. So, you can map this whole structure into a 5 input LUT, right. So, 5 LUT. And you can understand here there may be various possibilities here, right. So, you can suppose if you think about a 5 input LUT, so you can actually consider a structure like this also, right. So, this is also a 5 input LUT, right. So, here it is having 1 input 1 2 3 4 5. So, this is one possibility, or you can actually choose this, right. So, you can choose this also, this is also, then 1 2 3 4 5. So, you can understand that given a big logic circuit, the possibilities is very various, right. So, you can have different kind of this substructure possible, and also important that if you select one substructure, the next substructure will be different, right. So, if you just think about a circuit is, so if you just consider a circuit like this, suppose you have this, I am just considering some arbitrary circuit like this. You can see here, suppose I want to map this into 4 input LUT, right. So, if you just select this one, I select this one, right, then I have to select, so this is a map to 1 LUT, right. So, this is LUT 1. Now, I have to map some, because this is one output is common, I have to create another LUT here, right. So, just to map, because this is one output, it has to map here. Similarly, I have to map, so there are 2 out, so this is another output, so I have to map this structure. So, since this is already occupied here, there may be some duplication as well here, right. So, because I want to get another 4 input 1 output LUT structure here, so there may be some duplication as well, and also similarly, since this is one output, I can choose this one. So, this is one possibilities. Now, if you just think about, instead of doing this, I can, instead of selecting this, suppose I do not select this and I select, so I do not select this one, right. So, this is my structure. So, instead of selecting this, suppose I select this, right. So, this is also a 4 input LUT, right. So, this is 1, 2, 3, 4. So, now the next structure will be different, right. So, initially I select one possibility, I select this one, then I have to select something here and something here and something here, right. Now, if I select this one, now my choice will be different. Now, I have to select another LUT here, right. So, this is also one possibility. So, this is one possibility, right. So, this is okay, this is also not exactly correct because one output is here. So, I have to select this, right. So, this is 1, 2, 3, 4. So, similarly, I have to select something here like this, right. So, I have to select something here. So, the idea, the main point here is that there are huge number of possibilities and one choice uh, decide the next choice, right. So, the idea is that it is not, the choice is not unique, there are various possibilities and it is not like that if you choose something you have always a unique choice, right. If you select some other one way, the next choice will be different. So, the idea here is that there may be various possibilities and your objective would be try to map those whole logic structure, so that you all the gates of your design is mapped to some LUT and the your objective might be area minimization. Maybe that means you try to use the whole these things using minimum number of LUT, or you try to minimize the delay. The total LUT delay is minimum, or you have both, right. You try to optimize area as well as delay. So, your objective can be different, right. So, this is something very important and this is in general a NP-hard problem. So, usually all the synthesis tool you apply some kind of heuristic just to get a good mapping, right. So, so this is something and is important, that we cannot have a optimal solution which will give you the optimal mapping always, but some good solution, right, some heuristic based approach. Okay. And this is also I mentioned that there may multiple solution exist, multiple mapping exists and may differ in area and delay. So, we have to apply some kind of heuristic, some cost function just to decide that this is a good selection, this is a bad selection, this is better than this selection, and this we have to finalize the actual mapping, right. So, and also there is another important factor here. I will just give an example. Suppose I have this design, it is an interesting example. Suppose this structure I have given to you and I ask my LUT size is 2 input LUT, right, 2 LUT. That means the LUT have only 2 input, right. So, how many LUT structure is here and how many LUT is required to map this circuit and what is the delay, right. So, one possibility is that you map this into one LUT, right. You map this into one LUT because again 2 input, one map into this LUT, then you can map the whole this structure into one LUT because now this is also two input, and also similarly because and this is also into one LUT, right. So, how many LUTs are there? 1, 2, 3, 4, 5. So, implementation 1, I have 1, 2, 3, 4, 5 LUTs, right, 5 LUTs. On the other hand, and the delay is 3, there are 3 delay in any path, right, 1, 2, 3, 1, 2, 3. So, delay is 3 LUT delay, 3 LUT unit, right. So, this is the possibilities, but on the other hand you can actually map the whole circuit into one LUT, right, because if we just think about the whole circuit, I have 2 inputs, 1 output, right. So, implementation 2 is only 1 LUT is required and 1 LUT delay. So, you can understand. So, given such circuit, if you just choose this way, then I need 5 LUTs, 3 LUT the delay of the circuit is 3 LUT delay, and here 1 LUT and 1 LUT delay, right. So, the primary point here I try to say is that, so if you start from here and if you just identify a node and whenever you find a 2 input and if you stop here, so that means this is one cut, right. Cut is something you start from something and you find out whenever there is a k input is coming to that circuit, right. So, then this is a cut. So, if you find a cut of size k or say 2 here, if you stop there, then the kind of solution you are going to get may not be the optimum, because it may be at this point it grows high, right. So, if you just find a cut here, the input is 1, 2, 3, 4. So, I have a cut here which is basically of size 4 input cut, but which is not supported by my target architecture, because I assume ki my large structure is 2 input 1 output. So, if you just stop here, then you will end up having solution of this, but if you ignore that and if you go further, then you might have a reconvergence of path, right. So, this is what is happening. So, it grows and then it sink, right. So, if you have this reconvergence and finally you end up in a cut of this, the whole thing is also a cut, and this is a whole thing is also a cut, and it has 2 inputs, right. So, this is something also important. Sometime even if your target is 2, you may have to go further, because after some time you might have a reconvergence of path, and through which you can actually map a bigger circuit, a bigger logic into a single lot, right. So, this is something also possible. So, that is the core point or the key point is there. There are various possibilities and various way to actually identify the number of LUTs, and reconvergence is also important, and sometime some duplication also may happen. So, duplication when happen, if some node has a fan outs, then this node may have copied into 2 LUTs, right. So, this node is actually placed in this LUT as well as this LUT. So, this is called duplication. So, duplication is something should be avoided, because unnecessarily I am mapping these things to multiple node, right. So, this is something we will discuss further, how to take care of the duplication, how to take care of the reconvergence and the other factors. Okay. So, we will discuss all those things detail. So, before that, how to calculate the delay, what is the LUT delay. So, in this circuit you can see there is a path from here to here. So, this is the maximum longest path, and 1, 2, 3, 4. So, 4 unit of logic delays, right. So, logic gate delays in the normal RTL circuit, but if you map this into LUTs, what will be the what is the delay, right. So, this is something we are going to understand. So, suppose I map this into suppose my target is to 3 input LUT, right. So, 3 LUT. So, that means a LUT can have maximum 3 inputs. So, suppose I map this into 1. So, at this point delay of this is 1, right. So, this is the delay, optimum delay at this point is 1, because this is 1 LUT delay. So, now suppose I map this also into another LUT. So, at this point so I map the whole thing, this whole structure into 1 LUT, because now I have 3 input, right, 1, 2, 3. Then at this point also delay is 1, because though there are 2 gates, but at this point the whole thing is mapped to a single LUT. So, optimal delay at this point is 1. Similarly, if I just take this example, so here also the delay is 1, because this is mapped to 1 LUT, and now if I just take this I decided to map this whole thing into 1, then how we calculate the delay here? I will just find out the delay of all the inputs, maximum delay, and I just add one more delay here, right. So, this is optimal delay at this point 1, of this at this point is so this is not there, at this point optimal delay is 1. So, this should be optimal delay of 2, right. So, this is what is talked about. So, at this point the optimal delay would be 2. So, this is how I can actually identify the optimum delay of the whole circuit at the output, right. So, what is the maximum possible? So, given a mapping, what is the delay of that particular LUT mapping, right. So, this is we can actually identify, and which is basically nothing but the maximum delay of all the inputs, right. So, all the maximum possible delay of all the input plus 1. Okay. This is how we can actually estimate the delay of your mapping. Okay. So, now I am going to talk about this LUT mapping in detail. So, as I mentioned that LUT mapping is something we have to find out the cuts. Cut is something, a cut means what? A cut of size k means there are k inputs, 1 output. So, you have to first do all possible cuts in your design. So, cut enumeration. So, first step is something generate or enumerate all possible cuts, that is called cut enumeration, and the second step is that you try to cut select. So, there may be lot of overlapping and lot of duplication cuts and all those things. So, I have to find out the minimum number of cuts which actually cover all your gates, where we have minimum number of duplication, right. So, this is something called cut selection. So, there are 2 primary steps here, cut enumeration and cut selection. And as I mentioned, this problem is NP hard, we do not have a exact solution that the solution is this is the minimum possible mapping of the gates into a k LUT, right. So, we always have a heuristic based approach, or which is basically kind of iterative. So, you do some one mapping and then you try to do something, you try to change little bit, you go do another iteration, try to do some modification in the mapping, try to get a better result, right. So, this is what is called this iterative approach, right. So, what is happening here? So, if you have this non-critical path, so if there is a critical path here, so suppose this is the critical path, I cannot change anything here. Maybe something can be done for this node or something other nodes, right. So, which is not in non-critical path. So, their mapping can be little bit of change, so that I can have a better mapping, whether I can minimize more areas, right. So, this is something the overall idea, that I have one mapping and then I iteratively try to improve the area over that particular mapping, right. So, and one of the key factors is the duplication, how to remove the duplication, as I mentioned earlier also. Okay. So, let us go into this cart enumeration steps. In cart enumeration, the basic steps is like this. So, we process the node in topological order from the primary inputs to the primary outputs, and then combine subcart into create new carts, and also search for reconvergence. So, reconvergence example I have already given, that even if your target is to map the things into k LUT, but you should not stop whenever you find a cart of size k, because that may not be end of it. So, you might grow little bit further and then finally you might find a reconvergent path, and that will give you a better mapping. So, which I have already given example. So, I will talk about the other aspects. So, suppose this is my circuit. So, I will start from the input, right. So, this is my primary inputs and this is the primary outputs. So, this is Pi and this is PO. So, from where this I am going to start, right. So, as I mentioned, topological order from the primary input to output, and then I try to find a cart of my given size k cart, right. So, suppose I found a subcart like this. So, I found a subcart like this where I have 2 input 1 output. Similarly, I found another subcart of 2 input 1 output, right. And then I can actually combine these 2 carts because they have some input sharing, and I tend to create a cart of size 3, right. So, there are two input 2:1 cart, I can combine them to create a cart of size 3:1, right. So, this is what is called this, try to combine the subcart just to create new cart, because our objective is to create all possible cart of your design, right. So, and this is one of doing this. So, similar one example here. So, this is one cart and this is one cart, and since there is a one input sharing here, I can actually combine these two to get a bigger cart of size 4, right. So, this is how the new kind of cart will generate it. So, I will start from the inputs and then try to find out some carts, and our maximum possible cart is k. So, I will find all the cart of size k or less than k, and I can actually combine smaller cart where there are some input sharing to create a bigger cart as well. So, this is how we are going to generate all possible cart in your design. Okay. Now, the important factor is that, as I mentioned, the number of cart may be huge, right, and there may be lot of overlapping. So, which has to select. So, there may be say 10,000 possible cart has created, only 5, 10 or 20 has to be selected. So, which one has to be selected, right. So, that is something is important, and for that we should have some cost factor. We have to decide this is a bad cart, this is a good cart based on some cost, right, cost value. If the cost is less, that means a good cart. If the cost is big, that means this is a bad cart. So, how to decide a cost of a cart? Okay. So, that is something and based on that we are going to choose the better cart, right. So, that is given by this. So, there are 2 factors, cost contributed by the specific cart and the cost of the input, that I am going to discuss, right. So, suppose I have this cart, right. So, cart means what? 1 output and k output. So, cart of size k means there are k input 1 output. So, suppose this is my cart, this is the cart, and so I am going to talk about, you see in the next slide, that what is the component and the total cost of that cart, contribution from this particular cart, and this is from the input. So, what is this? What it says that the size of the input. So, I say this is a 4 input cart. So, there is 1 input, 2 input, 3 input, 4 input. So, now I am going to talk about the area of the input I, right. So, this is the area of the input I, because the input I also will be mapped to some other other lot, right. So, what is the area of that particular input and how many fan outs are there from this input, right. So, if this particular input is coming here and this fan out have some multiple fan outs, then this area has a contribution in this another cut here, another cut here, another cut here, right. So, this input will going to map into another cut also. So, that the effect of this area will be distributed among these 4, right. So, that is how this comes, that area of that particular ith input divided by the fan out value of that particular input, right. So, if the fan out is more, this will be less, if the fan out is less, then this value will be high, right. So, this is something how to tackle the input and how to handle the fan out of the input also, right. So, this is how we are going to handle the area. So, here one point to be noticed here is that only the cost is not associated with one card, because as this is interdependent, if we select one card, some way their input we have to select some other card from their input, right. So, from the input of that card. So, since the dependency between the cards are there, so we have to take care of the cost of the card itself along with the associated the inputs and outputs, the associated or the surrounding cards also. And what is the surrounding cards? Those are the inputs, right. So, from the inputs, what is the area and their impact on that particular cut, and if that input has a higher fan out, that means this has a less impact, because that is a good selection, because now I can use this card output to multiple cards, right. So, this is something we can do. So, this is how this first factor comes. Okay. So, then we will talk about this cost of that particular area card of the card itself. So, okay. So, that I am going to discuss first. So, the first thing is here is like, suppose the factor is like, suppose this is my card. Okay. So, key parameter is the card size, card size of IC. So, that means card size is the number of input, right. So, if I just select a card like this is the card size, right. So, this is the card size IC. This is the number of inputs, right, and then NC is the number of node inside, right? The number of node inside is the NC by the card. Okay. And then the FV is the fan out number of the root node. So, the output node, what is the fan out? So, there may be multiple fan outs here, right. So, this is the fan outs, this is FV, right, and this is IC. So, for this card I have 2 input, right. So, this IC equal to 2 here, and what is the NC for this card? NC for this card 1, 2, 3, 4, 5, 6, right. So, there are NC is 6 for this card, and FV there are 3. So, FV equal to 3 for this cut, and then PF is the duplication cost. I will talk about that. So, the cost contribution from this particular card is given by this factor. Okay, this is the primary factor. So, it's saying that IC by NC plus FV. What does it mean? So, more nodes in the graph, that means it's a good cut, right. So, if you pack more nodes in a particular card, that means a good card, because you are trying to pack many or big number of gates into one card. So, this is a good cut, and as I mentioned, if the value is UC is low, that means a good cut. So, that is why this come into the output, right, in that here. Okay. And also as I mentioned here, if there are more fan outs from this output, so this card will be shared among multiple cards from here, because I will have another card here, I will have another card here, I will have another card here. So, this card will be shared among all this. So, that means it has a positive impact, because one card I am going to reuse in multiple places. So, that also reducing the cost factor. And if and this is, so this is IC is the number of card size. So, the cost of that particular card is given by IC by NC plus FB. You can understand, if the number of node is big, now FB or the fan out from this node is big, so this value will be less, right. So, this is something. So, so that will become a good cut. And the other two factor is something I will talk about now, which is basically duplication cost. Okay. What is the duplication cost? So, you can see here, suppose this is my F node, so root node, right. So, root node is the last node, and if the input of this is F1, this is F2, right. So, the input of that root node, and from here, this is very important things to notice. If there is a fan out, right. The problem here is that if there is a fan out, there is no output from this cart, because a LUT has one output and k input, right. So, since this is my output, this output is not available. Once you map this cart into a single LUT, this output is not available, right. So, this is very important. So see, but this is going to use in somewhere else, right. So, this fan out is going to use somewhere else. So, the problem here is that means this node has to be duplicated in some other cart. So, for this, whatever the cart I am going to generate, I will just draw it, so you will understand. So, let remove this. So, the problem here, as I mentioned, the only output is available this. So, this is not an output available to us, right. So, now, but this output is going to use some other nodes. So, whenever I am going to decide a cart here, this node has to be duplicated for this cart, because this node is not available for me. Similarly, if I am going to for this also I am going to have a this node has to be duplicated, right. So, this is the problem. So, if that particular root node, the parent node, that previous node of the root node has multiple fan out, that is actually bad thing, because if has multiple fan out, that has to be duplicated in different other cart also, which is actually unnecessary. So, that has a negative impact. So, this PF is given by this. So, as I mentioned here, so this is given by this. So, so the F1 and F2 I talked about. So, this is so in general this is F. So, the number of node in that particular cart at the input, and this IC is the size, right. So, if the point is here that if there are number of nodes is here is high, then the possibility of duplication is also high, right. That means this is a larger duplication cost, and this IC is the normalization factor. So, as I mentioned here, if that particular in the cart, so we always consider sub cart here, right. So, if in the sub cart of this input F1 has more number of nodes, that there is a high chance that some of them will have a fan outs, and that will create a duplication. So, that means it will increase the cost of that particular cart. That means it is a bad cart. The basic idea is that if you select a cart and if the internal node has some fan out, that is basically redundant thing. So, that node has to be duplicated for some other cart. So, that means you should not choose this kind of cart, you try to avoid this choosing this kind of cart, because this is something there are lot of node will be duplicated in some other places. So, that will increase the cost. As I mentioned, the low cost is good. So, if there is no such fan out, this will be 0. So, there is no impact of that. So, the cost will be less. But if there are lot of nodes, then the cost will be high, there is a high chance of duplication. So, we try to increase this cost of this particular cart, and we try to mention that this may not be a good cart. Okay. So, this is how we are going to handle this duplication. Okay. So, this is something we talked about. So, there are three aspects here. The first thing is that we generate, we will start from this primary input to output, and we choose the subcut. We combine the subcut to generate a new cut, as I mentioned here, and then also we try to remove the duplication, avoid the duplication, this way just to increase the cost. And also as I told, the reconvergence also has to taken care, that example I already given. So, these are all these things we are done iteratively just to find out all possible cut, so that I get all possible cut of your in a design, right. So, once we have generated this, the next step, and as I mentioned, the cost is something is given by this factor, which has impact of that own factor, the size from the cut size, and that fan out of the internal nodes, that will come into picture, as well as the factor is from the input also. If there are some input which has multiple fan out, which is good, right. So, if, as I mentioned again, that if the output of a cone, if the output of a cone has multiple fan out, which is a good thing, because this is a good cut, because this result we are going to use somewhere else, because none of the node will be duplicated here. So, since this is one output, this will be one cut, this will be one cut, this will be one cut. So, this is going to be a good cut. So, in a good cut, if the fan out of that root node is high, that means a good cut. But if there are some internal node have a lot of fan outs, which is bad thing, because those node effectively will be copied to somewhere else, and which is result in a lot of duplications, and most likely have number of more LUTs, right. So, this is basically a bad cut. Okay. So, once you have done this, we have to select, right. So, we have to going to select the cut, and the cut selection, as I mentioned, we have again this is something a heuristic algorithm is happening. So, our objective is try to cover all the gates of your design using minimum number of cut, okay. Or maybe you try to area is minimized or your timing is also minimized, okay. So, that is something has to be there, and the choice here is that if there is a critical path, I just show how to calculate the delay. Once you have some choice, you just select some cuts, you can find out the delay. So, whatever in the critical path, that cannot be changed, but if something lies in the non critical path, there I can actually make some choice, some alternate, so that I can improve the area, okay. So, usually it happens in iterative process. So, I create one solution, then try to improve the solution in every iterations, and there are some other factor also which is important, right. As I mentioned that this cart are interdependent. So, once you select any cart, I associate some cost with it, right. So, using the logic I just defined in just previously, right. So, every cart has a cost, but and once we select a cart, and so that actually makes some changes in the surrounding carts, because maybe some fan out is now going to consider, some will be ignored, some will be considered. So, they have some impact on the surrounding carts. So, that is something called local cost adjustment. So, once you select a cart, we enumerate all the cart, I associate a cost of that cart using this function, right. So, this function using this function, okay, sorry, using this function, okay. So, every cart has a cost, but once we select a cart, so because I generate all the cart, after now I am not going to select all the carts, I am going to select some of them. So, once I am going to select some cart, then it has some impact in the surrounding carts. As I mentioned, the actual cost also involves the input fan out in fan out of the internal node, fan out of the output node. So, all are actually making effect on the actual cost. So, once I select some node, it may have some impact on the surrounding nodes. So, that has to be adjusted. So, that local cost adjustment is that. So, for that I have to consider the input sharing, slack distribution and cart probing. I am going to discuss those have an impact on the cost, and I am going to update the cost of the surrounding cart using this logic, okay. So, here is the overall algorithm. I am going to go into briefly. So, this is that iteration, right. So, you can see in the within the iteration, this is the one loop in which I am going to do one choose one solution. I am going to get one solution, and I am in the outer loop I am going to select multiple in iteration I am going to generate multiple solution. I am going to improve the solution, okay. As I mentioned, the start is starting from the POs, the primary outputs. The cart selection start from the primary output, okay. So, my L is that list of POs, primary output of your circuit, and then I just find out the required time using some analysis, that what is the optimal timing, depth and all those things using that logic. And then what I am going to do, I take one output and then I pick a card, because from that card, so suppose this is my circuit, I took a output node, right. So, this is my output. So, from this in the enumerated list there may be many cards, right, maybe 10, 20, 50 cards possible, starting which has the output this. So, from that I am going to choose one card which has the less cost. I am going to choose the cost which has the less cost, which is a good card. So, once I choose that, so this is the one lot I have already decided, right. So, suppose I choose this card. So, suppose I have two input output initially. So, my PO has only two, this and this. So, I decided to choose this, right, and it has a 4 output. What will happen now? So, now I am going, so my list will include by this input of this LUT V. So, this is my LUT V, right. So, I am going to choose this LUT V because this is a good cut starting from this. So, once I have done that, now I have to choose some cut from this input, right. So, now my L will consist this, right. So, initially I have these two. Once I have selected this cut, all the input will also become the primary output now, because this is already decided. Now, I have to select some cut from starting from this node of the cut where the output of this is this, right. So, this is how the whole thing works. So, whenever I am going to choose this one, my cut set will become this followed by this and this, right. This is how the whole thing works. So, every iteration I am going to select one cut and I am going to update that PO list, that is the logic I define, and also this I have to also do this I have to do this update profile as well as this update required time, as I mentioned using this local cost adjustment. because some of the other cart will improve with this selection. So, this I am going to discuss. So, this is what is the one iteration through which I am going to okay. So, as I mentioned, once you select a cart, we have to update the surrounding carts, update this timing profile info using this local cost factor we are going to discuss now. And this, so after this while loop I have one solution, right. So, this is one cart, this is one may be selected and so on. And once we have this, then in the next iteration whatever I am going to, when I am going to talk about this timing information and all, I am going to talk about the timing information of the previous selection, so that I can decide whether my current iteration is better or not, right. This is how the whole algorithm works. Now, if you just think about that local cost factor, one of them is input sharing, which is very important, and I also mentioned earlier also. So, suppose I have decided this is one cart and this is one cart, right. So, this is one cart and this cart is shared in many places. Now, once I start from this, so just to elaborate this example, suppose I have this, so I have decided this cart and then say suppose from this input I have selected this cart as well. Okay. So, this is something I never know which order it will go. So, suppose I have selected this one. So, now if I start from this node and if I found that one of the I saw a cart where one of the input is coming from one other cart which is already selected, right. So, that CW, then this cart is a better cart, right, because this particular input is sharing among multiple cart which is already decided. So, there is a high chance that the duplication will be less here. So, in this case I am going to improve reduce this cost of this cart further, right, because I am now in this particular cart where I have already selected these two cart and I found for this cart one of the input coming from already a cart which is selected. That means, if I select this cart, there is a high chance there is no duplication through this, right. So, then this is something is a good cart. So, I am going to improve the cost of this particular cart further, so that chance of getting selected of this cart is high, right. So, this is what is called input sharing. So, if this input is coming from already selected cart, which is should be a good cart. And I mentioned also that if a cart is selected and it has multiple fan out, that means this is a good cart. So, it has a positive impact in LART mapping. Okay. So, this is what is called input sharing. So, if we found something, then I am going to reduce the cost of that particular cart further, so that chances of getting selected of this cart getting high. Okay. This is called input sharing. And then the slack distribution. So, how so suppose I know for this time from the timing information I need the required timing here, the data should come at here by this time, right. And now, if we found that the arrival time of the input, the max of arrival time is that, right. So, that max of arrival time. So, this the largest among this is this. So, now the slack is what? The required time minus this, right. So, if I found this at this point, if this is 0 less than 0, that means this is not a possible factor, because the data is coming later than what is the expected. So, this cart should not be selected, right, because this is not a feasible cart, because if you select this way, if the data will come here later than the expected required time. So, but if it is positive, this is that positive, this value is positive, that means it is actually a good cart, because I have some additional time here which I can utilize to have a different selection, so that I can reduce the number of areas. So, I am going to further reduce the cost of that particular cart if it has a positive slack by a constant factor. So, this is something is the local aspect, right. So, if I just find the timing of this particular cart is positive, that means if you are going to select, I have some extra time to select something else. So, I am going to increase the chance of getting it selected by reducing the cost of that particular cart further, right. This is what is called slack distribution using local cost during local cart adjustment. Okay. And also this cart probing, which is also an important factor. I mean, if I just found if a particular node, as I mentioned, if there are multiple fan out, which is bad thing, which is already taken care of that. But if I found some node where all the fan outs are part of the same cart, so this is one cart, and from this fan out both are coming here, right. Or you can think about, this is my whole this is the bigger cart I have selected, and where the internal node has fan out, which is a bad thing, but fortunately all the fan outs are a part of the same cart, so which is a good thing, right. So, that means it is not going to increase the size, it will reduce the duplication, and also positive thing is this is a kind of a reconvergence, right. So, it will improve the number of node getting selected inside that will be high, right. So, that is the point, that if all the fan outs are internal and is part of a card, which is a good thing. So, I am going to reduce the cost of that particular card further, so that this make it better card. Also, if the so the other example that I just give here, for this card, if I found the input the multiple input coming from the single source, which is also good, right. So, that means which is also good, that means I am not going to select all of them are coming here. So, the high chance is that this the number of input of this is less, because now I can consider both of them as a single input and I can select something else as well, right. So, this is also most cost saving. So, this is also have a positive impact on the cut. Similarly, the number of reconvergent path. So, if I found something which is going further and then slowed down, similarly there are two reconvergent path here. So, if the number of convergent path is high, that means circuit has grown and then reduced, right. So, which is a good thing. So, that means the possible of number of gates that is getting mapped into this particular cart is high. So, again all these three aspects actually improving the getting chance of getting selected of this cart is high. So, I am going to reduce the cart cost of that particular cart further using all this scenario, right. So, this is something I am going to do it locally, because and now this is also decide about the current scenario, because once I have selected something, the next iteration I am going to update this, because I know now the surrounding things what is happening there, right. So, this is all these three, this cart probing, this slack distribution and the input sharing is the three factor through which I am going to improve the factor of the cost of the cart locally, right, and during the iteration, and this is how that this is how the whole selection algorithm works. Okay. So, this is how the whole thing works, that I start from the output. I am going to select a base cut, but I am going to select this peak cut. I am going to update I consider all this local factor like input sharing, slack distribution and this cut probing to update the cost, and I am going to select the best cut. Once I have selected that, their input will become the PO now, right, because this is selected, their output will become PO, and then once this is selected, their output also input will become the next starting point. So, this is how the whole algorithm works, and finally, I am going to select cart which will cover all the gates of your circuit. Okay. So, this is what is LUT mapping all about, and as I mentioned that if a node has high fan out as a root is of a cart, which is a good choice. A node with high fan out at internal node is a bad choice, because high chance of duplication is there, and our objective is to try to reduce the duplication as much as possible and try to map the whole thing in minimum number of LUT and minimum number of delay. Okay. So, here is a summary that FPGA technology mapping is little bit different from ASIC mapping, because here we have dedicated resources like LUTs, DSPs and RAM, and our objective is to map the whole thing in these particular blocks, and this DSP and RAM inferences usually happen during pre-mapping stage. So, that because we have to preserve those structure, so that does not get flattened or dissolve into the gates, so that DSP or RAM inference cannot happen. And LUT mapping is a hard problem, computationally hard problem. So, we usually we apply the heuristic based approach, and there are two steps primarily here. One is cart enumeration, second is cart selection, and we also applied several kind of other factors, cost factor like reconvergent of path, avoid duplication, input sharing, cart probing and those kind of techniques, just to readjust the cost and try to select the best cut. Okay. So, this is the overall summary of this technology mapping of FPGA. Thank you.